couple of quick announcements for AICHE. Again, both of these links will be posted along with the lecture, so you don't have to try to scribble them down right now. But they've got their family blanket set up, family banquet scheduled for this Friday, 5 to 6. I can only assume that it will not involve, yeah, it's virtual meeting. I didn't think it would be like literally showing up for a banquet. And then they'll have a social on the 29th. Is the midterm meant to be out of 30 points? It should be out of however many points all of those add up to. So if there's a discrepancy, I'll have to go back in and double check it to work it out. I think it's supposed to be out of 40. So if on Canvas it's showing out of 30 and on Gradescope it's showing 40, it should be the one in Gradescope. It may just not have translated correctly from one to the other. But the Gradescope one should be the accurate one. And then, as I said previously, we're going to catch up with homework. What are we on now? I think homework 6. So homework 6 is going to be on our packed bed reactors. And it will cover packed bed reactors in general, all of our packed bed reactor stuff. And let me pull up our syllabus really quick. This is where we're going to catch up the time because we've been pushing homeworks back. But we're also going to catch up the time in the sense that it's not going to be a full problem set. So there will not be as many problems on this one. So this one will be due at the end of Friday. 11 o'clock. So the homework for homework 6 will be just 2 problems, right? So we're going to keep that one quite a bit shorter, and both of them essentially only have one calculation to do on them, because I promised you I wouldn't do like a part A and a part B and a part C and a part D and a part E. So they're all just one calculation, except for the first one, which it actually does have a part A and a part B, but there's no calculation to do on part A. I just want you to watch a chemical safety board video that's related to an accident that happened with the chemical that you're going to produce in that problem. So, okay, I kind of bent the rules a little bit there. Yeah, there is a part A, but there's no calculation. I just want you to watch the video and answer a couple of basic questions like what happened, right? What went wrong on something like that. So that one will be up probably after lecture today. Today's topic, and really the rest of the week's topics, if you look at our syllabus, we're just looking at special cases of the packed bed reactor all of this week, which actually I guess we could do a poll. So we have, let's do a poll anyway. Monday, May 25th, we have off because that is Memorial Day. So there will be no lecture on May 25th. Might as well add that on here. So no lecture on May 25th, which is a Monday. And so right now the schedule says that we have lecture 32, which they are really adding up right now, is on Friday, 22nd of May. And that's also when homework 6 will be due. So 11 p.m. on Friday. And then we skip it down to Monday on the 25th of May. That's Memorial Day, so we don't have any class then. And then lecture 33 will be on Wednesday, the 27th. This is also the date homework 6 due, homework 7 out. So there was always intended to be a gap between when homework 6 was due and when homework 7 went out. And the reason for that gap was to try to give you that whole long weekend, right, where you don't have to do any homework or anything like that. However, we can do a a poll in here, which is a simple poll. I'm not going to use the actual polling thing. Let's say in the chat, would you like to move homework 6 due date to the 27th? Because we won't actually move and lose any time there. We'll still be right on time. It's just you'll kind of have to work on homework over the weekend. So, do you want to push hard to get it done before then, or would you prefer to spread it out even more and go out to the 27th? So over in don't use chat for this, use the participants window where I can actually see the counts. Use the participants window and say yes if you would like to move the homework date, and no if you would like to keep it on the 22nd. Participants window, not the chat. You won't get it. There will be no problems added to it. It's not like there's more that's going to be added to it. Boy, that's right down the line, isn't it? It's 24 to 18. 25 to 17. No, it's exactly the same assignment. I will not add problems to it just because it's due a few days later. It will be exactly the same assignment. All right, so I think that kind of set it up a little bit. So right now we've got 29 saying, yes, move it to here, and 16 saying, no, leave it here. So the yays have it. Yeah, if you want to turn it in early, go for it. You can absolutely have it. But fine, we will move it to the 33rd lecture, which is on the 27th of May. So it'll get bumped back there. Again, no new problems will be added to it. It'll just be due on Wednesday. Cool. So with that, we can go ahead and get started on today's topic. We're just looking at PBRs, packed bed reactors all week, looking at kind of special cases of it. There's really only one really new special case for the packed bed reactor, and that's actually what I want to spend the first 20 minutes or so of class going over. Is almost all of the special cases of the packed bed reactor or the plug flow reactor are actually still doable in a packed bed reactor with very little change to them. So let's look at different special cases. And then we'll look at what those special cases look like for a plug flow reactor, which is stuff that we've already seen before. And then we will compare what that special case for the packed bed reactor looks like. So the packed bed reactor special cases are given, I believe, in chapter 10 of your book. And then the special cases of the plug flow reactor were in chapter 8 of your book. And so I'll give equations and numbers where we can. So the two first special cases that we had for plug flow reactors was if we wanted to write the material balance in terms of conversion, in terms of XA. So remember, this was only valid if we had one reaction. But so often we can model a system with just one reaction, or one is the most important reaction, that's not a bad thing to kind of keep in the back of your mind. Like, yeah, I can simplify things if I write them in terms of conversion. And the material balance for this was that dxa dv was equal to minus RA divided by NA0, which, if you've ever looked at your notes, like I thought I was getting okay at using this Wacom tablet, and then I looked at some of my notes, it still looks like a child's handwriting to me. That is problem 8.2, or excuse me, equation 8.2. And then if you compare the packed bed reactor version of the material balance in terms of conversion, it's dxa now dw is equal to minus RA prime divided by NA0. Right? And then this one was equation 10.2 in your book. And so we can see a lot of similarities between the two of those, right? The biggest changes are we went from V over here to W over here, and we went from a plain old RA here to an RA prime over here. The difference between the primed and the unprimed variables is the prime variables are the same variables without the prime, just divided by the density of the bed. And that tends to pop up wherever you have the V's going to W's. Any of them written in terms of W's often have the primes floating around on another variable somewhere over on the other side. Similarly, the energy balance written in terms of conversion. So if you can write the material balance in terms of conversion, you can usually write the energy balance as well. If you have to write both, it tends not to be, I think, particularly faster to solve the problem. There are some special cases that unfortunately we don't have time to get to this quarter, because there's a global pandemic. So we moved a little bit slower. There are some really interesting things that you can do in terms of conversion when you're dealing with multi-reactor systems. But for the most part, it doesn't change. There's nothing that you can do with the full equations as well. So the energy balance, if you're interested in that stuff too, look at the multi-reaction chapter in your book. dt dv, the denominator down here was kind of a mess. It was the inlet molar flow rate of A times the theta I term, CPI, and then minus the conversion of A divided by the stoichiometric coefficient of A times delta CP. And then on top, it was delta Q minus R delta H. Right, and there was no sum in the numerator for R delta H because there's only one reaction. That's the implied behavior of this is that there is no second reaction. Let's see if I can. I've never tried to do this. Oh, that's so perfect. I'm sure you can do that on your paper as well. So this equation was 8.3. And then if you needed to do it for the packed bed reactor, very little of it changes, right? Instead of the V down here, you change that to W, and then you add a prime to the delta Q and to the R. And actually, I like that method of highlighting just to show you the difference between the two. So I'll do that on the top one as well. And so this equation is 10.3 in your book. Let's make that red since the other labels are already red. Prime, W, W, prime, prime. Right, so those look very, very similar. All of the same approaches that you would have for a plug flow reactor trying to solve that sort of a system, they're going to work for a packed bed reactor too. The only difference is you'll have those primed variables, which means the row bed is floating around. But row bed is a constant. It's just a number. And we're going to look at an example of row bed here in a couple of minutes. For the jackets, right, we're going to have either a co-flow jacket or a counterflow jacket. Y'all are my fika today, by the way. We are having fika right now. This is relaxing, right? Writing these equations. The temperature change of the utility inside of the jacket for co-flow and counterflow in a PFR was either plus or minus delta Q on top. So it was a minus if it was a co-flow and a plus if it was a co-flow or a counterflow, times whatever the flow rate is of that utility divided by its heat capacity. And so these were 8, 15, and 17 in your book. For the packed bed reactor, almost identical. You just change the V to a W. Change the V to the W, just like I said I would. And then it's still plus or minus a delta Q divided by NU CPU. And there's a prime on the Q. Right, so the prime on the Q means take the same Q that you had before, divided by row bed, which is a constant. You've got yourself a Q prime. These are actually not in your book. But if you need it, that's how you get it. And then the last one where we're going to spend our time today in the last 30 minutes or so of class is what the pressure drop equations look like, for very good reason too. The pressure drop in a plug flow reactor, which again, keep in mind, a plug flow reactor is a tube. It's an empty pipe, and then you flow gas through it. You got yourself a plug flow reactor if something happens inside of there. Was minus the volumetric flow rate, so that's a lowercase v, times the friction factor, which is F, times this other set of constants, 128 times total mass flow rate, divided by pi cubed, times the diameter of the tank, or diameter of the reactor to the 7th power. This was equation 8.11. The change for the packed bed reactor is a little bit more than what we're used to. If you compare what kind of changes do we have to take for the material balance, the energy balance, the jacket, all of those changes were very minimal. The changes to the pressure drop are a little bit more extensive because flow around what we call submerged objects. So the submerged object there is your catalyst particle. It's submerged because the flow is going around it on all sides. So we call that flow around a submerged object. The pressure drop here starts with dP/dW. And then it's equal to the same minus V, so minus the volumetric flow rate, times the friction factor. But that friction factor is not the same friction factor, so we denote that with a subscript P for particle. So the subscript there is a P, and it stands for particle. And we use that subscript a few more times. The numerator in the top is not identical. It's 64 instead of 128. MT divided by pi cubed. Diameter is changed. It's no longer to the 7th power. It's now to the 6th power. And there's a new diameter sitting in there, which is diameter of the particle. And it's just raised to the 1. So the subscript P on the lowercase d sub p means diameter of the particle. It also has the rho bed term sitting in it, which is over here. Right, there's quite a few more variations on that than there are on any of the other ones between a packed bed reactor and a plug flow reactor. The reason for those are mostly historical. The folks who were worried about pressure drop in a packed bed were generally not the same folks who were worried about pressure drop in tubes. They were related because they were both in fluid mechanics, but at some point those two fields diverged. And so the types of expressions that we have for the friction factor here are generally not the same as the types of expressions we have for the friction factor over here. For some reason, when they do the F sub P, the general standard for everyone is to just drop a couple of coefficients along the way. And that's why we have a 64 here and a 128 here. Had everybody gotten together and talked about it before they wrote these, we could have done 128 for both. But they were sort of developed in separate. And so it's not that we can't do the math to make them look a little bit closer. It's that if you do that, your definitions won't match everybody else's, and it'll be really hard to go back and forth between the two. And a factor of 2 on there for a pressure drop, if you mess up the 64 to the 128, that can be really big. And so it's better to just leave these a little bit different so that our representations can look more like everybody else's representations. So let's talk about those friction factors really quick. These tend to be where things look nasty. So the friction factors for the plug flow reactor were pretty simple, right? We said almost all of them can look like 0.0791 divided by the Reynolds number to the 1/4. this ends up being a constant, right? Is the row bed part of the equation? Yes, so that row bed is multiplying here, right? It's on the left-hand side, it's out in front of the dpdw. So if we're gonna solve for dpdw, you tend to have to move it to the other side, but it's all usually written this way. I think it's written that way to try to keep this term looking as close to this term as we can, like within reason. So they just I moved the row bed over to the other side. Right, and so this friction factor is 8.12 in your book. And so whether the system is reacting or not, it doesn't matter if it has a reaction in it or not. This value for the friction factor is constant. The reason being the Reynolds number is a function of the total mass flow rate, and the total mass flow rate is always constant, assuming you just have one big tube. The pressure drop depends on whether or not there's a reaction, because this term, the V in here, right, that will change if there's a reaction. But the friction factor itself, just the F, that's constant. And then the friction factor for a packed bed, I am going to move this one over because it tends to be kind of long. So F sub P, this is called a particle friction factor, and it's designed for flow through a packed bed. Whether there's a reaction or not, this will hold. And it's kind of lengthy. 160 plus 3 times the Reynolds number divided by 1 minus phi. Phi is, remember, our void fraction of the bed, raised to the 0.9, and then multiplied by 1 minus the void fraction squared, divided by the void fraction cubed, times the Reynolds number. This, in your book, is equation 1017. And it's referred to as the KTA equation. KTA because the German government, the arm of the German government in like the 60s and 70s, came up with this for pressure drop across packed beds inside of nuclear reactors, which is obviously important, right? Because the stuff running through a nuclear reactor is the coolant. And you really got to know what the coolant flow rate is through a packed bed or through a nuclear tube, a nuclear reactor's fuel tube, because that's important. You don't want to mess that up. There's another very common version. I would say it's actually more common, which is 1016, which is the Ergun equation. The problem is the Ergun equation, although more common, is less accurate. It was designed for a much smaller range of flow rates, and it was like back in the 40s or something. KTA was like, I want to say 70s or 80s, and so it's a little bit more, it's not a little bit more, it's much more accurate over like 4 orders of magnitude larger values. It's more accurate. And so a reasonable question when you see an equation like this is, where in the world do they come up with that? This part over here, that part is basically a geometric factor. And then something called a characteristic I'm just going to move that down because I'm not going to be able to spell it that. Characteristic force. So a characteristic force, if you haven't taken 101A yet, you'll learn about it in 101A when we talk about dimensional analysis. Oftentimes when we look at a problem, we can say, I expect certain forces, certain length scales to be on the order of a certain value. And so we can estimate that the usual amount of kinetic energy associated with a flow often looks like a 1/2 mv squared kind of thing. And so we can say, you know, the total kinetic energy has to look something like a fudge factor times this 1/2 mv squared thing, because we know most of the time it comes in units that look like 1/2 mv squared. And that kind of analysis is something that you'll see in 101A. And so these terms, the 1 minus phi squared and the phi cubed times the Reynolds number, those are coming from those sorts of arguments, which is we expect it to behave in a particular way. The forces for both drag and pressure drop, we expect them to behave according to a certain scale. And so if you play around with that scaling argument, which is done in your book, if you want to see where that comes from, you can do the algebra to back out these numbers. This part, though, is not. This is the part where it says, like, yeah, we can get close. We can get the general behavior with the other part. This part is determined experimentally. Right, so the KTA folks, they had lots of beds of their nuclear reactor fuel. They would flow material over them like a water for a coolant, figure out what the pressure drop looked like, do it lots and lots and lots of times, and find out that turns out all the friction factors kind of obey this similar form. Ergun did exactly the same thing, right? Ergun started off with the same form. He just came up with a different fudge factor. It was 150 instead of 160, and there was no 3 and no 0.9. Or I think the 3 was a 0.75. Anyway, if you compare the Ergun equation to this one, they end up looking pretty much the same. It's just the coefficients are different. So regardless of whether it's an experimentally determined coefficient or not, it works very well. And with something as complicated as flow through a packed bed, experimental is the best you're ever going to get. It's not something that we can easily simulate or calculate from first principles because what we call the length scales are so many. The flow around a surface has interesting features that are on the order of like millimeters, and then the particles are on the order of centimeters, and then the bed is on the order of meters. It's very hard to put all of that together in anything that's not just an experimental approximation. But if you can do it, do it. There's probably room out there for folks who can do that experimentally, or excuse me, from first principles. So let's take a look at one of these things. Because I'm a person interested in chemical engineering, among other things that I have in my garage are packed bed reactors. This is a packed bed reactor, which I think you can see in front of me here. So what we've got here are copper particles, which I'm going to bring my leg up because this thing's actually pretty heavy. There we go. It's filled with copper particles right now, and they're quite heavy. Up on the top is a little plug up here that keeps the particles from coming out. And then down here in the main space of the tube are the copper particles. So let's put this a little bit closer just so you can see it. Oh no, I knocked my microphone down. So those are the copper particles in there. Those are what we mean when we're talking about particles inside of a bed, right? If you remember my nerds example, those are about the size of one of the larger nerds. And so these are on the probably about the average size for most packed beds. They probably have something like this. And then the packed bed is rather long, right? It starts off here, and then it goes all the way up to about here. It actually goes into the bottom a little bit. So this whole area down there is the bottom. And that brass part here, let me move it around. This brass part here is where the fluid would come in. So it would come in through here and then go up through your packed bed to actually react something. So this is what an actual packed bed reactor could look like. It's on the small side for industry scale packed bed. That packed bed is also designed to be operated vertically instead of horizontally, but just to save us some problems here, we're going to imagine one that's operated horizontally, but we're going to use the sizes that I just came up with here, the one that I just showed you here. Yeah, in that case, the copper would act as a catalyst. So the little copper particles are inside of our tube here. The reason I'm switching it from horizontal to vertical is because I don't want to worry about the effects of gravity. You are more than welcome to turn your reactors vertical if you want to. That is not a problem. It's just that the math, now you have to talk about gravity as well. And I don't really want to worry about that right now. So the bed length that we had in that one that I just showed was 18 inches. So if I measure from the bottom of the spheres to the top of the spheres, it was 18 inches. The diameter of the bed from here to here was 44 millimeters. And then if you look at the particles themselves, those were copper spheres. The diameter of the particle here was 1/8 of an inch, and it was solid copper. And so what are some of the things that we could calculate? Oh, I should also mention that 18 inches of spheres, if you were to take those that packing out of there and measure its mass, the mass of the catalyst here, we also call that the mass of the bed. It's the same thing, right? What's the mass of the particles that are sitting inside of there? If you were to measure it for that particular bed, which I happen to have a scale in my garage, is 3,300 grams. That's all true, by the way. I know sometimes people are confused, like, is he being sarcastic? Or does he actually have these things? I actually have those. They're sitting down in my basement right now. So what are some of the parameters, right? Now that we've got a picture in our mind, a lot of these parameters can be calculated just from this information. We could go look up what the density of copper is. The density of copper here would refer to the density of the catalyst. And so if you look that up, it's 8,960 kilograms per cubic meter. That's pretty dense, right? Water's 1,000. It's not the densest one that we've ever had, but it's pretty dense. The volume of the bed, which is our classic V. So this would be the same V that we've seen before, but it's also sometimes called the volume of the bed, V sub bed. That would just be equal to 1/4 pi d squared L, which in the numbers that we've got here are 1/4 pi. The diameter that it's referring to is the diameter of the bed, which is 44 millimeters, right? This 1/8 of an inch up here, actually, I don't know if I have that calculated as no, I don't. I didn't convert it there. It's the 44 millimeters, right? Not the 1/8 of an inch, because the 1/8 is the diameter of the particle. And then the length of the bed is 18 inches. And so if you calculate a volume from that, it's 6.952 times 10 to the minus 4 cubic meters. But I'm going to write everything in base SI units because eventually we'll need it, right? So the 3,300 grams that we've got up here is the same as 3.33 kilograms. And now we can calculate the density of our bed, row bed, as simply the mass of the bed divided by the volume of the bed. And the mass of the bed is 3.33 kilograms divided by 6.952 times 10 to the minus 4 cubic meters. And so we end up with 4,790 kilograms per cubic meter. We can calculate from that, if you recall from the very first discussion of packed beds, that the void fraction was 1 minus phi times rho cat is equal to rho bed. From that, we already know the density of the catalyst is 8960 and the density of the bed is 4790. And so from that, we can calculate that phi is 1 minus the rho bed over rho cat, which is 1 minus 4790 divided by 8960. And here it's about 0.465. Right, and so that phi parameter comes up a lot, right? Here's our phi, there's its value. So those are all sort of like geometric type parameters, right? Parameters that come up a lot with these sorts of problems. And that's how they relate to like an actual system, right? The one that I was just holding in my hand. Suppose the flow is water at 2 gallons per minute. Right, and 2 gallons per minute is 1.26 times 10 to the minus 4 cubic meters per second. I'm sure you keep that conversion factor in the back of your mind. If that's our flow, how do we then calculate the Reynolds number and the particle friction factor? Whoops, there's no reason for that. If you wanted to do that, we now have enough information on here. So our Reynolds number is equal to 4 times the total mass flow rate divided by pi times the diameter of the pipe times the viscosity of the fluid. The total mass flow rate is rho times V divided by pi d mu. And since it's water, we know that the density is 1,000 kilograms per cubic meter. The volumetric flow rate, we just calculated, or we were told it was 1.26 gallons, or 2 gallons per minute, which is 1.26 times 10 to the minus 4 cubic meters per second. And then we have a liquid here. So pi is always pi, no worries about that. The diameter is 0.44 meters. And the viscosity for a liquid for this class will always be 10 to the minus 3 pascals dot seconds. Right, that number is always either 10 to the minus 3 or 10 to the minus 5. It's minus 3 if it's a liquid, it's minus 5 if it's a gas. And then the result here is a dimensionless number, 3646. And that's our Reynolds number. So again, I was careful because I make the mistake regularly, to keep the kilograms per cubic meters to match the pascals, the seconds, the cubic meters, and the seconds over there. The result is a number that has no units, which is the Reynolds number. And now we can plug all of this into our friction factor expression. So F sub P for a particle friction factor, remember, is 160 plus 3 times our Reynolds number, which is 3646, divided by 1 minus our our void fraction, which is 0.465. That is all raised to the 0.9 power. And then that quantity is multiplied by 1 minus 0.465 squared divided by 0.465 cubed times the Reynolds number, right? Kind of a pain in the neck to track all that stuff down, 3646. But also notice that it's constant, right? Everything that's in here is a constant. The Reynolds number up here is constant because the total mass flow rate will always be constant. And then the void fraction 465 is also constant because that's describing how the particles are set inside of the tube. And so assuming your particles are not moving, which you've got a problem if your particles are moving, then this will be a constant. So this is a constant, and you can just calculate that. It will end up being a number, which is 6.706. It's also non-dimensional. Right, it has no units associated with it. In the same way that the Reynolds number has no units associated with it, the friction factor also does not have units associated with it. So finally, with that, we can then calculate our pressure drop expression as dP dW is equal to minus the volumetric flow rate, so 1.26 times 10 to the minus 4. I'm going to leave the units off here because they're all SI, times the friction factor, 6.706, divided by the density of the bed, which we had calculated previously to be 4790, multiplied by 64, because that was the funky little constant that we had, times the density of the fluid, which is 1,000, times the volumetric flow rate, 1.26, times 10 to the minus 4, divided by pi cubed, times the diameter of the tank or the reactor, which is 0.44, raised to the 6th power, which is, I think it's cool whenever you have 6th and 7th powers, and then multiplied by the diameter of the particle. So the diameter of the particle was our 1/8 of an inch, which we have to convert to meters, which is 0.032 meters. if you were to carefully look at the units on here, the units on here end up being pascals per kilogram of catalyst. That's important. You should go back through here and show that these are the units, because the kilograms can cancel out. There's no reason that the units have to be written like this, because there are 2 kilograms floating around, but we choose to separate the kilograms, right, between kilograms of catalyst versus kilograms of fluid. Technically, the kilograms are canceling out, but we have opted to leave one of them there so that we can express this as pascals per kilogram or kilogram catalyst. So you should check that. Shouldn't the equation be multiplied or divided by density instead of multiplied? The density I think you're referring to is this one, which is rho bed, and it is being divided by that. This density is the density of the fluid, and the reason that we've got that is because I went from the total mass flow rate to being rho times V. So it's 2 different densities. The 4790 is the density of the bed. And so the dPdW here is just equal to a constant minus 1.99 times 10 to the third pascals per kilogram catalyst, or minus 1.99 kilopascals per kilogram cat. This only happens, it only looks this nice when it's non-reacting. If it's a reacting system, there's usually a V that's floating around inside here, and it's not so simple. You can integrate this, which again, the integration part is usually not what you can do, or you can't do the integration if the flow is reacting. You have to use ODE45 to solve it, but this is a non-reacting flow, so we can just integrate it directly. What you'll find is that the pressure at any point in your pipe is equal to whatever the initial pressure was, minus 1.99 times W. So usually the step here is use ODE45, right? It's very rare that we get an actual expression that we can evaluate here. Typically we have to use ODE45, but I wanted to point out something that's very important here, is that this expression implies a potential problem. So if we have this as our plot, and we have our W in kilograms of catalyst down here, and we have our pressure over here. Suppose we come in at P0. This equation suggests 2 things. One, it's a straight line, which is not always the case. Yours will generally not be a straight line, but this one happens to be a straight line, so it's easy to draw. So the other thing that it implies is that it's got a negative slope, so it's going down, right? You start from P0 and then you go down. So I'm going to do my best here to draw a straight line. That's not bad. The slope of this is minus 1.99 kilopascals per kilogram of catalyst. There are 2 important things that just happened here. One is this point is 0. This is vacuum, as in like the vacuum of space. In fact, even less pressure than the vacuum. Space has a very tiny pressure. The 0 that we are referring to here is perfect vacuum. If there is absolutely nothing here, this suggests that if you come out to here, at this particular point, which happens to be 258.7 kilograms of catalyst, that is the biggest the reactor can be. Right? You cannot expect to flow 2 gallons per minute of water with that particular particle size, with that particular tube size, at that particular flow rate. You cannot flow it through a system that has more than 258.7 kilograms of catalyst. That is a fundamental limit. It cannot go any more than that, not the 258. The point where the pressure crosses 0, that is the most that you will possibly get. There's another limit, which is here, which is at 1 atm. This is a practical limit, right? Whereas 0 pressure is what we call a fundamental limit. You cannot do it. There is no means by which you can do that. If you get to here, this is a practical limit, right? This is 207.8 kilograms. The reason that 1 atm is a practical limit is because if anywhere in your system you ever need to go lower than 1 atm, this is called what's operating under vacuum. Oddly enough, it's actually above the vacuum point, but that's the way it goes sometimes. So you are operating what's called under vacuum here. This is super expensive, right? You have to seal the whole system exceedingly well and then put a pump on it and pull on it to actually get the pressure to go below atmospheric pressure, right? That's what you're experiencing right now is atmospheric pressure. If you are attempting to run your reactor such that the outlet is below 1 atm, so this region over here, or actually let's highlight that. If you are trying to run your reactor with its outlet over here, it's not that it's impossible, right? This is physically possible. It's just really expensive because now you got to put a pump on the other side to pull that stuff through, right? You can no longer get it to just push through. You have to actually now pull on it because you have gone under atmospheric pressure. And so it's not that it's impossible. It's just super expensive to do something like that. And I know I'm at 351, so I'm going to stop. I'm just going to sketch what our problems tend to look like. With a reacting system, it tends to look the same, except it just kind of falls like that. It doesn't curve back on into itself like that, right? This tends to be what a reacting system looks like. Same idea, right? The curve just has a different shape to it. So there's usually a practical limit of 1 atm, which is the lowest pressure you can go, but there is a fundamental limit of P being 0, where you cannot go any lower than that. And that can set limits on what you can do with your reactor. So it's 352. The homework 5 or homework 6 is going to practice this. We're going to practice this stuff for the rest of the week. The homework bumps back to Wednesday, but there are no new problems being added to it. So hopefully that'll give you some breathing room on there. So thanks, everybody. Apologies for the 2 minutes over, but as usual, I will stick around and answer questions. Please stay safe, and we will see you on Wednesday. Let's go ahead and get some Kevin running in here again. Let's do sneaky snitch instead. I like that. Part C, you can just summarize them. It's okay if you have a drop in the middle of the iteration graph. It doesn't have to be smooth. That's not uncommon for iteration procedures to sometimes sort of get lost over in one area and then recover and come back. That's what that spike is. Question regarding example on page 252. Let me pull that up. So there are two examples on page 252. If you're referring to example 9.2, like the very end of it, there is a row bed in there. And then for 9.3, so for 9.3, there's sort of an implied row bed because the equation is written as KCA. And so the row bed can be inside of that K, which is not uncommon for packed bed systems, is to just absorb the row bed into the K, which usually gives it weird units. And so that particular problem works out down on page 254. You'll see that the K over V naught has units of per kilograms of catalyst because the row bed was absorbed inside of that K. Sometimes they don't. They'll just give you the K or give you the rate already in terms of kilograms of catalyst, and then there may not be a row bed. How do you get Y7 calc to be a 1/12 vector? Every Y7 through there should be a 1/12 vector. The reason being there are 12 components, so the Y it contains all 12 of the components. So if you did a calculation where you have a 1/12 vector going to a 1/1 vector, something got dropped. Because that 1/12 vector is the composition of the concentrations of all 12 components. If MATLAB told you it was 1/1, it very well could be 1/1 in your calculation. It just means there's an error with the calculation. The relationship between Q2 and Q3 is the same one that we always use for liquids going in and out of a CSTR. So on 264, I see that we have not assumed that it's constant. maybe the question on page 264 about why it was constant, we started out assuming it was not constant. It just so happens from the setup of that problem that because all of the reactions are 1 plus 1 and 1 goes to 1 and 1, so there's no net change. And then it's also isothermal and isobaric, so the volumetric flow rate will end up being constant, but we didn't start off with the assumption that it was constant. For question 4, if you're using my rate function, they ought to be really close. If you're using yours, it could be off a little bit. But if you use my rates function inside of fsolve with the same initial guesses that I used, which I think I suggested that you use the inlet stream as your guess for the solution for fsolve, those ought to be really, really close if you're using my function. Yeah, sharp dips in the convergence graph are fine. So if your convergence graphs your iteration is here and your COD is over here, and they look something like that, that's perfectly fine. So the question about why 7 having 1 or 2 or whatever, when you say it looks like you're writing y7 calc of I12 is equal to y7 calc. The problem would be this one, right? Specifically the 12. You're just saving a particular value of y calc, or maybe it was the other way around, right? Maybe you had it reversed like this. What you might want to do is something like y7 calc of row I, but all columns, right? Not just the 12th one, but all of them are that value. I'm not sure if it's on the left or the right, but something like that. The COD to use is the one that's in stream 4. Sorry, the COD to use is the one in stream 4 for problem 5. The COD to use for problem 4, there's only one. Like the COD for the inlet has already been given to you. The COD for the outlet is something that you'll have to calculate. But the only one that's meaningful is the one that's out here at the end of your iterations. These. All of the CODs that you're calculating to build up the rest of this plot, those are just intermediate calculations. So none of those matter. The only COD you're interested in is the last one. And then, yeah, so if you're referring to COD for problem 5, then you would be looking at the COD just for stream 4, which is the outlet stream. No, if you don't have this dip, that's okay too. If you don't have that, that's fine.